Hello everyone. In this video, I'll solve few more problems related to finding rank and nullity of a linear transformation. In the last video, I had explained what is rank and nullity of a linear transformation, and I had given you examples where the transformations were simple. If the transformations are not simple, so in that case is how to find out rank and nullity of a transformation. Let us see that. See here, find basis and dimensions of kernel and image of the following transformation. This is the given transformation. You know that dimension of kernel is called as a nullity or null space of the given transformation, and dimension of image of the transformation is called as rank of the transformation. So you have to you know that kernel of a transformation and image of a transformation both are subspaces, means they are the vector spaces independently. So if they are vector spaces, then they should have a basis, and number of elements in a basis is called as dimension of those vector spaces. So let us find out that first. First we have to find out kernel of f. Kernel of f means what? All those vectors which map to 0. Means we have to find out all those vectors which map to 0, 0, 0, because the second vector space is R cube under the transformation f. So that implies x plus 2y minus 3z equal to 0, 2x plus 5y minus 4z equal to 0, and x plus 4y plus z equal to 0. What is this? This is a set of a system of equations. This is a homogeneous system of equations, and it is denoted as ax equal to 0. Now, to get the vectors which map to 0, 0, 0, then you have to solve this system. How to solve this system? You have to find out rank of the matrix A. If it is less than n means number of variables, then you always have a non-trivial solution. Non-trivial solution exists. Because you know that for a system of homogeneous equation, there is always a solution. 0 is always solution of this system, which is a trivial solution. Other than 0, do you have any solution? That you have to find out. Okay, for that you need to get the rank of this matrix A, coefficient matrix. If it is less than the number of variables, then non-trivial solution exists. Hence you can find out the kernel of the transformation. So let us do that. First let us write the coefficient matrix. So first equation coefficients are 1, 2, minus 3, then 2, 5, minus 4. Third equation 1, 4, 1. You have to transform this matrix to the row echelon form. So how will you do that? R2 changes to R2 minus 2R1, R3 changes to R3 minus R1. You have to make these two entries 0. So which is 2 minus 2, 0, 1 minus 1, 0. So 1, 2 minus 3, 2 minus 2, 0, 5 minus 2 into 2, 4. 5 minus 4 is 1, minus 4, minus of minus plus 3 2 is 6, which is 2. And here 1 minus 1, 0, 4 minus 2, 2, and 1 minus of minus 1 plus 3, it is 4. Now again you have to reduce it to the row echelon form. This is the first non-zero entry of second row, below which the entry must be 0. R3 changes to R3 minus 2 into R2. So no change in the first row, no change in the second row. Third row changes as 0 minus 0, 0, 2 minus 2, 0, 4 minus 2, 2 is 4, 4 minus 4, 0. Done. It is in echelon form now, row echelon form. What is number of non-zero rows? There are 2 non-zero rows, correct. Now how many variables? N equal to 3. 3 variables x, y, z. So rank of A is less than number of variable, hence non-trivial solution exists. So non-trivial solution exists. Therefore, how to find out that non-trivial solution? So now this column corresponds to x, this is to y, and this is to z. Pivot means first non-zero entry of any row. This is the first non-zero entry of first row. This is called as pivot. There is a pivot in the first column. Now this is the first non-zero entry of second row. Okay, third row is not having any first non-zero entry. So this is pivot of a second row. So second column has pivot, first column has pivot, this third column has a no pivot. No pivot. Whenever there is no pivot, such a variable is called as a free variable. Z is free variable. Free variable means you can take any value for Z. So therefore Z equal to, you take it as some value k, that is free variable. So then you will get y plus 2z equal to 0 equations, this, and x plus 2y minus 3z equal to 0. So corresponding to the first row, this is the equation. Corresponding to the second row, this is the equation. Third row is free variable. Z is free. So y equal to minus 2k you will get, because I have taken z as k. Then x equal to minus 2y plus 3z. So that is x equal to, put y equal to minus 2k, 2 to the 4k plus 3 into z is k, 3k. Therefore x equal to 7k. Hence you got x is 7k, y is minus 2k, z is k. So I want all those x, y, z which map to 0. Therefore I get kernel of t, kernel of f equal to set of all x comma y comma z belongs to R cube. So t of x comma y comma z equal to 0. T is f here. Okay, so which vectors map to 0 vector? I got here now kernel of f as 7k, then minus 2k, z is k, belongs to R cube, this vector, such that k belongs to R, any value, any real value. So this is the kernel. All those vectors which are in this form belongs to the kernel of this transformation. Means when you give k equal to 1, you will get 7 minus 2, 1. Then k equal to 0, 0, 0, 0, which you already know, 0 vector always maps to. K equal to minus 1, minus 7, 2, minus 1. So all these map to 0. T f of this goes to 0. F of this vector, f of this vector, all these map to 0. So now you need to find, this is the kernel of the transformation. You have to find out dimension of and a basis for this transformation, for this kernel. See, k is common, you take it outside, you will get 7 minus 2 and 1, such that k belongs to R. So every vector of kernel f is a linear combination of 7 minus 2, 1, because k into this vector. Therefore 7 minus 2, 1, the vector having 7 minus 2, 1, this serves as a basis. And how many linearly independent vector in a basis? Only 1. So dimension of kernel of f equal to 1, because there is only one linearly independent vector in the kernel. So we got the dimension of kernel of f is equal to 1. Now you have to find out dimension of image of f. Dimension of image of f, which is nothing but rank of f, equal to how much? For this we need to make use of the proposition. If v1, v2, so on up to vn spans the whole space v, if span of these vectors equal to the space v, then span of their images, t of v1, t of v2, so on up to t of vn, that is equal to image of the transformation. If f is a transformation from v to u, linear transformation from v to u, and you have a set of vectors which spans this space v, then the images of these vectors spans the image of the transformation, image of f. Let us make use of this. The transformation given here, f is transformation from R cube to R cube. Okay, so you know that standard basis spans the whole space R cube. Therefore 1 0 0 0 1 0 and 0 0 1, this spans whole space R cube. Span of this equal to whole space R cube. As per this proposition, span image of these vectors spans the image space f of 0 1 0, f of 0 0 1. these vectors, span of these vectors equal to image of the transformation, image space of this transformation. So what is the transformation? F of x comma y comma z equal to, the transformation given here is this. I will write here once again, that is x plus 2y minus 3z, then 2x plus 5y minus 4z, comma x plus 4y plus z. This is the transformation. Now let us find out what is f of 1 0 0. So x is 1, y is 0, z is 0. So you will get 1 2 1. Then f of 0 1 0. So here y is 1 now, the x and z are 0. So you get 2 5 4. Substitute here, x equal to 0, y equal to 1, z equal to 0. F of 0 0 1 equal to, z is 1, minus 3 minus 4 and 1. So these three vectors now span image of the transformation. Okay, now you have to check, are they linearly independent? Because if three vectors span whole space R cube, then you know that those three vectors can be considered as basis. But they are not spanning the whole space R cube. They are spanning the image space. Image of this transformation can be equal to R cube or can be a subset of R cube. Therefore, now we have to check, are these three vectors linearly independent or not? I can't conclude this itself is a basis. I have to check, is it linearly independent or not? How to check, are these vectors linearly independent? Always you have to go with the row echelon form. So 1 2 1, write the given vectors as a row of a matrix A, 2 5 4, minus 3 minus 4 1, then convert it into row echelon form. If you get any 0 row, that means these vectors are not linearly independent. If you get all three non-zero rows, then the vectors are linearly independent. Let us check that. 1 2 1, reduce it to R2 changes to R2 minus 2R1, R3 changes to R3 plus 3 into R1. So 2 minus 2 0, 5 minus 4 1, 4 minus 2 which is 2, then minus 3 plus 3 0, minus 4 plus 6, 3 to the 6 which is 2, 1 plus 3, that is 4. Now again 1 2 1 0 1 2. Here R3 changes to R3 minus 2 into R2. So 0, 2 minus 2 0, 4 minus 4 0. So you got 1 0 row. Means all these three vectors are not linearly independent. Only the first, this is 1 2 1 comma 0 1 2. These two vectors are linearly independent. Or you can take these first two vectors 1 2 1 2 5 4. These two are linearly independent. Anyway, I have taken it in the echelon form. Whatever vector you get in the echelon form, you can take those vectors. So 1 2 1 0 1 2. These two vectors are linearly independent. Hence, these two vectors form basis for image space, image of F. How many elements in the base is 2 elements. Therefore, dimension of image of F equal to 2, which is nothing but rank of F. Okay, so you can verify rank nullity theorem also. Rank of F plus nullity of F equal to dimension of R cube. Is it true? We got rank of F as 2 plus nullity of F we got it as 1. So which is equal to 3. Rank nullity theorem is also verified. So this is how you find out dimension of image of the transformation and dimension of the kernel of the transformation when the given transformation are not simple transformation. Finding kernel is easy, see, because these this is the procedure. You have to get the solution of the homogeneous system. But here in image of F, while finding image space, because image of F looks like this. Okay, you can't directly solve it as if you go as per the definition. Okay, what is the definition of image space? All those vectors of the second vector space for which there exists a pre-image. Correct. Now, but you can't go with that definition. You have to make use of this proposition. If a set spans the space V, then the image set of those spanning set vectors will span the image of the given transformation. So you can always go with the standard basis here, because standard basis not just spans the space, it is linearly independent vectors as well. So here now, after applying the transformation, okay, where these standard basis vectors will go, you got 3 vectors now. Now these 3 vectors spans the whole space image of F, but we need the linearly independent vectors. Then only that becomes basis. See, you know that when you have 1, 2, 2, 1 and 4, 2, this set spans R square. Okay, if you add more and more number of vectors in a standard basis or any 2 bases, that definitely spans the space, but are they linearly independent or not? That you have to check. See, any 3 vectors in R square are always linearly dependent. So though I have added this vector, span of this may merge with the span of the one of the vector, hence that spans the whole space R square, but it is not linearly independent. It can't be considered as base. Now these vectors spans the whole space image of F, but you have to check, are they linearly independent or not? For that you have to write a matrix A with these vectors as its rows, then convert it into the row echelon form. If row echelon form gives all non-zero rows, the 3 vectors are linearly independent, but here they are not giving you non-zero rows. 1 0 row you got, means the third vector can be eliminated. Hence only these 2 vectors are linearly independent. Therefore these 2 vectors span the whole space image of F, as well as they are linearly independent. Hence this set forms a basis for the given space. Hence number of elements in the base is 2, dimension is 2. Don't write dimension of image of F as 3. Once you get the spanning vectors, you have to always check, are they linearly independent. If they are linearly independent, then only they form basis. Therefore these 2 vectors form basis. Hence dimension of image of F equal to 2. See, let us take up one more problem. This is the transformation G, that is transformation from R cube to R square. Okay, so you have to find out the kernel of this transformation, image of the transformation, then dimension for kernel of the transformation and dimension of image of the transformation, as well as a basis for kernel G and image G. So let us do that first. First let us find out kernel of G. Okay, for that you have to equate the given mapping to 0, 0, 0. Kernel means what? All those vectors which map to 0 of the other transformation, not 0, 0, 0, 0, 0, because the second vector space is R square. So here this implies x plus y plus z equal to 0 and 2x plus 2y plus 2z equal to 0. G of x comma y comma z is nothing but this. This is to be equated to 0, means first coordinate equal to 0, second coordinate is also equal to 0. Now this is a homogeneous system, Ax equal to 0. So the coefficient matrix easy now, 1, 1, 1, 2, 2, 2. Reduce it to echelon form, 1, 1, 1. R2 changes to R2 minus 2 into R1. So 0, 0, 0. So this is rank of A equal to 1, which is less than number of variables. Number of variables equal to 3. So you have one more proposition, like if you have 2 equations in 3 variables, then it always has a non-trivial solution. If m is number of equations is less than number of variables, then that system always has non-trivial solution exist. Okay, directly you can apply that also. Rank of A is equal to 1, which is less than number of variables, hence non-trivial solution exists. So therefore kernel is not just a set containing 0 vector, other vectors also map to 0. So which are those vectors? Let us find out. Now check here, there is a pivot in the first row. This is the first row. First non-zero entry of the first row is 1. So this is called as pivot. There is no first non-zero entry in the second row, no pivot in the second row. Go column wise. This is for x, this is for y, and this is for z. There is a pivot in the first row. There is no pivot in the, there is a pivot in the first column. There is no pivot in the second column, no pivot in the third column. Therefore, these two variables are free variables. If there are no pivot, then those variables are called as free variables. So y and z, these two are free variables. You can give any value for them. Then x is dependent on those. X plus y plus z equal to 0. As per the first row, the coefficient of x, y, z like this. So x equal to minus y minus z. Y, z are free, correct? No, you take y equal to k1, z equal to k2. K1, k2 belongs to R, any two real values. As per that, then x becomes minus k1 minus k2. Therefore, your kernel of G equal to set of all vectors x, y, z belongs to R cube such that t of x, y, z, t means here G equal to 0, 0. Okay. So kernel G becomes now, what are those values of x, y, z which map to 0? So x is minus k1 minus k2, y is k1, okay, and z is k2. K1 comma k2 belongs to R. Okay. Let us simplify this. This is equal to k1, you take common, so you'll get minus 1, 1, 0 plus k2 from the second vector, then you'll get minus 1, 0, 1. You have to search for the coefficients, that's it. K1, k2 belongs to R. Here, look here, this entire kernel is a linear combination of these two vectors. Okay, and you know that these two vectors are linearly independent as well. Okay, these two vectors are linearly independent as well as they span whole space kernel G. Hence, you can say minus 1, 0, 1, then minus 1, 1, 0. This is a basis for kernel G. And how many elements in the basis? Dimension of kernel G equal to 2. That is nothing but nullity of G. So we got the nullity of this transformation. Now we have to find out image of G. Okay, how to find image of G? V1, V2, so on up to Vn. If these vectors spans the space V, then their image spans the image of the transformation. So the transformation is from G is from R cube to R square. Take standard basis of R cube, G of 1, 0, 0, where the standard vectors will go after applying the transformation. What is the transformation? X plus y plus z. G is, I will write here, x plus y plus z to x plus 2y plus 2z. 1, 0, 0 goes to 1, comma 2. Then G of 0, 1, 0 goes to y is 1, 2. Then G of 0, 0, 1 goes to 1, comma 2. Now, these three vectors are the images of these standard vectors. So these three vectors spans the image space of the transformation. So span of these three vectors equal to image of G. But you know that you can't consider dimension of image of G as a 3 because these three are same vectors. That means I told you in the previous example, you always have to check are they linearly independent. Same vectors you have, they can't be linearly independent. So this becomes 0 0, this becomes 0 0. So only one non-zero vector you got. Only this vector is linearly independent. So span of 1 comma 2 is equal to image of G, and just 1 comma 2 is also linearly independent. Hence what is the dimension of image of G? Dimension of image of G equal to 1. There is only one element in the basis. This 1 comma 2 acts as a basis. Now though these three vectors, they are the same vectors, span whole space image. Spanning means what? Alpha into 1 comma 2 plus beta into 1 comma 2 plus gamma into 1 comma 2. Okay, so linear combination of this, that is nothing but 1 comma 2. If you take alpha plus beta plus gamma, that is one more variable you can take, one more coefficient, you can take it as delta into 1 comma 2. So all these vectors span image of G, means the single vector also spans image of G. So for a basis, all these vectors repeated 3 times not necessary. The same vector it is, so one time it is enough. So dimension of image of G is equal to 1, because you have to check are these three linearly independent. These three are not linearly independent. Only single vector if you take, then it becomes linearly independent. So 1 comma 2 spans the image G as well as that is linearly independent. So number of elements in the basis is 1. Hence rank of this transformation is 1. You can verify the rank nullity theorem as well. Rank of G is 1 plus nullity of G is 2, which is equal to dimension of the first vector space R cube, that is nothing but 3. So this is how we solve problems related to finding kernel and image of a transformation. Hence the rank and nullity of the transformation when the given transformation is not simple transformation. I hope you understood the concept. Thank you for watching.